Okay, so in this lecture here, in this video, the main focus is going to be on working through examples of applying these kinetics, force mass acceleration relationships for rigid bodies. Okay, so our general procedure I have written here, and then a summary of our equations of motion that we derived last time. So maybe we start down here, right? So this is what we basically derived last time, and it's putting it in a nice clean summary. These are going to be the equations of motion that enter number 3 here. Okay, so our translation equation of motion, right? That's just Newton's second law, force equals mass times acceleration applied to the center of mass. This is truly two equations because there's a horizontal and vertical component. And then we derived rotational versions of that, force equals mass times acceleration, because they're rotational, right, with the cross product of the force here. We have moments on the left-hand side, then balanced by the rotational version of mass and acceleration, angular acceleration, and then the resistance to rotation is this moment of inertia. Okay, so we got our, and now because of these are all planar motion, right? So everything is assumed to be in 2D planar motion here. These equations, they're vector equations, but they're really only there's only one equation here, and that is the k-hat direction. Okay, and that's because the acceleration is in a plane, is like in the plane that we usually look at. The position vector is in that plane, and so the cross product has to be out of that plane. Here we have the acceleration vector that's always wrapping, and then therefore the axis about which it wraps around is out of the plane direction. And then our moments always act out of the plane. Okay. Let's see, we have 3 different versions of our rotational equation of motion here, and the idea is we choose one to add to these 2 translational equations of motion. Choose one based on what the system setup is, based on what would be convenient. All right, so one of them is for just arbitrary point O. The next version is if that O is a fixed point, we just basically drop, well, these 2 terms combined into where we can use the moment of inertia about that O point, whereas here we're using a moment of inertia about G, and so there's parallel axis theorem used to go from the first one to the second version. And the third version is where it really comes from this one, where that arbitrary point is no longer arbitrary, but it's the center of mass, and that center of mass could be moving around. Right, so those are our 3 versions. Okay, so now let's get back up to here, right? So the procedure we're going to follow for the examples to follow here. These now, again, limited to solving rigid body dynamics problems where we're using force-mass acceleration relationships. All we're doing is differentiating between the procedures that follow this section, which is when we get into work energy and we get into using momentum. Which we've already talked about for particles. The next step is going to be talking about those for rigid bodies. But other stipulations for this procedure are these types of problems. Rigid body dynamics for those rigid bodies in planar 2D motion. We won't get to 3D motion until the last section of the book here, last section of the class. And yeah, and then they're involving rotational and translational versions of this force mass acceleration relationship. All right, so this first step will always be drawing a free body diagram, right? Get all the forces on there. Going to be absolutely vital. We're also going to put all the moments on there. So this is forces and moments. Okay, are put into our free body diagram. Next, we write down any kinematics, if we need to, and this would be to get relationships for the acceleration of the center of mass for the rigid body, the angular acceleration or angular velocity, anything else that's maybe there's velocities like translational velocities need to be related here. And then also any geometrical properties could fit into here, right? So do we need to measure where the center of mass is? Do we need to know where G is first, right? Or do we, based on what comes to follow, should we be calculating the moment of inertia about the center of mass axis, or should we be doing about a different axis, right? Then we write up to 3 equations of motion based on the choices here, what we talked about here, and then solve for the unknowns based on all that, right? And along the way, we're always checking, like, how many unknowns do we have based on how many equations I've written? Did this equation help me, or did it add more unknowns? Good idea to just start writing down relationships, know that they're right and they're valid, and then just count up the number of relationships and how many unknowns you have. As soon as you have enough equations to solve for those unknowns, then it's just solving a system of equations. All right, so let's dig into the first one. Okay, let's get started on this one. Now we've got two slender identical bars in this example that are welded together. They each have a length of 1 meter and they each have a mass of 5 kilograms. Welded together in this shape, put into this position where we've got a pin here at A which allows rotation only in this direction, and then released. And we want to know is what's the angular acceleration of the bar at this time instant, and then the reaction forces up here at A that's holding the pin in place, that's pinning that, right? So let's start with a coordinate system, right? It's going to be a convenient choice to put a coordinate system here at the pin. So let's label that as O, and so the coordinates there are X and Y, so Z kind of comes right out at us. As we did previously with our center of mass, where we have to determine that first. So let's first start by labeling our identical bars as 1 and 2, so we can work through them. So this will be 1, this will be 2. Let's put some distances on here. Okay, so they're each 1 meter. Okay, so that's 1 meter, and then so is, I think I could sneak that to there. That's also 1 meter. Great, so in determining the center of mass, we need to find, we need to label the center mass of each one, right? Well, that's right in the center for these slender rods. And at some point, right, we will be combining these and finding a center, right? And not maybe sure where to go. Is it going to be at this corner? Is it going to be way down here? Let's let the math just tell us where it is. Okay, so let's first start by doing step 0 here, which is geometrical properties. Geometrical properties. And what we mean by this is we're determining the center of mass and then the moment of inertia. We'll need that for this rotational motion when we get to our equations of motion. Okay, so we choose point A as the origin. So I labeled that O. And then we'll find the center of mass, G. Okay. Remember, this is center of mass. And the notation we give is G. Okay. So X bar, in terms of the XY coordinate system, right, that is going to be how far do we have to go. And I won't label this. I don't want to confuse this too much, right? So in terms of its X distance, number 1, right, the first slender bar up top here is a half backwards. So this is minus 0.5. It has a mass of 5 kilograms, right? And then this one here, its X location is 1 down, right? See this distance here to get there? We have to go 1 to the left and then half down. I think I might have misspoke. So minus 1, let's say this is plus a negative 1 times 5. Okay, and then divide by the total mass, which is just 5 plus 5. We get negative 0.75 meters, which is somewhere right there. All right, and then our Y bar, the Y location of our center of mass, well, number 1 center of mass is at Y equals 0 in terms of the O coordinate system there. So this is 0 times 5, and then this one we had to go down a half. So minus 0.5 times 5. All over the total mass, 5 plus 5. And so we got a half of 5 divided by 5 plus 5. That's a minus a quarter. Okay, so minus a quarter is right there. So our composite center of mass, so the center mass for the entire shape, sits right there, not even on the object, right? So this is G. Okay. And then determine moment of inertia. Now the moment of inertia here, right, we worked through examples in the past of this. Let's see, right? The way we do this, we add up the component parts. So this is going to be the moment of inertia about point O is the for the composite shape is the moment of inertia about point O for 1 plus that same thing for 2. So I O for 1 plus I O for 2, right? Which these we can number 1, taking it independently, that's just a slender rod pinned about one end. And we know that formula is ml squared over 3. So we've got 5 times 1 squared over 3. Okay. This is a slender rod pinned, or about an end. Okay. Let's go. Can we write this slender? I think I've run out of space, so let me make this arrow tighter. Okay, this is slender rod about end. Okay, fit it in there. Now, IO2, that's going to be a slender rod, right, where we don't have the luxury of having it about an end or about the center of mass. So we need to use a parallel axis theorem here, right? So we'll do this, the moment of inertia about the center of mass, which is ml squared over 12, ml squared over 12, and then we need to add the moment of the parallel axis term. Now the parallel axis term, right, we need to know the distance away. That's this diagonal line here. That distance is, well, let's see, what is that distance? Let's see if we can fit it in here. The distance here is going to be, well, that's the hypotenuse, so that's going to be the square root of 1 squared plus 1/2 squared, which is 1 1/4. Sorry, distance squared is 1 1/4. We can just keep everything distance squared. Well, no, we'll keep it like that, but the reason we keep it as distance squared is it shows up in our parallel axis theorem, right? Oh, I put the whole formulas down here. This is ml squared over 3, all for object 1. Okay. This is ml squared over 3 for object 1. Now we have ml squared over 12 plus the mass times the distance from the center of mass for object 2 here to the point of interest, which is O. This is all for object 2. Okay, so those are our formulas. We're plugging things in here. Now this is plus 5 times this 1 1/4. Okay? And we don't square that. That is d squared. Right? We kept it d squared there. Okay, so this turns out to be, well, that's 5 over 3, so 5/3. This is 5 over 12. And then we've got 5 times 5 over 4. Can we work through this? Let's see. So this is going to be, let's see if we can work through this. So this is going to be, it looks like the common denominator here is going to be 12 across all of this. So we have, let's see, 5 times 4 over 12, that's 20 over 12, plus 5 over 12, plus this is 5/4, so that's 25 times 3 over 12. And let's see, this is 75 plus 5 is 80 plus another 20, that's 100. We've got 100 twelfths, and divide the top and the bottom by 4, and we've got 25/3. Okay, so then our moment of inertia is 25 over 3, or 8.333 kilogram meter squared. Okay, so this is with the parallel axis theorem on that second one. Okay, great. We got our geometrical properties now. And that's going to be a value we'll use. All right, so let's get into the actual kinetics portion here, right? Which means we'll start with the free body diagram. This is step 1. Okay, step 1. Free body diagram, which, let's see, we have our L shape, we have the center of mass there, and we've got a location there. Forces on it are up here at A, right? Could be a Y reaction force, an X reaction force, and it's pinned, right? So it can rotate about in this plane here. And there is our mg. Now this is the total mass applied at the center mass. So this is 10 times 9.81 meter per second squared. So this is going to be 98.1 newtons. Okay, so just be careful here. Once you get to the center of mass, this is the total mass, not, right, it's like maybe confused because we have m equals 5 there. We're not referring to that m. Okay, and that's it. No other forces. Okay, so now let's move into kinetics. That's step 2 in our procedure. Yeah, let's just use a new color. Kinematics, description of motion. What can we say? Well, we're looking here for the angular acceleration of the bar, so we're going to need to involve acceleration. So let's see if we can relate the acceleration of our center of mass, g, okay, to the angular acceleration of the origin, of point A here. Okay, so let's write it as the acceleration of the origin, or we could have put A there as well. So this is going to be the acceleration of the rigid body crossed into the relative position vector of g in the primary from point A, or the origin of the coordinate system, minus omega squared r. There's that position vector again. Now we ask anything we can cancel out here. And yeah, well, this is a fixed point, right? Right there, that's a fixed point. So that's 0. All right, it's pinned. And then the other thing is it's at this snapshot that we need the angular acceleration. So right now this is 0. Okay, it starts from rest. So it's not rotating right now. It will about to rotate because there's going to be a non-zero acceleration. So this is the only term that's non-zero. Okay, so then we have our acceleration of point G equals alpha k hat. We got planar motion, so all of the acceleration is, into or out of the board here, crossed into the relative position vector of g with respect to O. So here, right, that's what we calculated the center mass. We have to go backwards. I mean, these are basically these quantities. Backwards 0.75, down a quarter. Okay, so negative 0.75 I hat minus 0.25 j hat is that position vector. And let's see, now we've got k, all right, so again, I'm going to do this from my perspective, and you have to mirror me. K, all right, so kind of go towards you, mirror you, so you should be pointing towards you with your fingers, crossed into I hat, that's a positive j hat in the positive y direction. Okay, so we've got AG is now, so that's the j hat term, so that's negative 0.75. Actually, let's put them in order. So we'll put the I hat component first. So I know we have one coming, was the second term. But the j hat component will go over here. So it'll be minus 0.75 alpha j hat. What's that other term? K hat crossed into j hat. Point to yourself. K hat, j hat is upward. That points, our thumb points in the negative I hat direction. But this is negative, so that's going to turn that positive. Positive 0.25 alpha I hat. Okay? 0.25 alpha I hat. Let's write this out. 0.25 alpha, I just didn't give myself enough space there, minus 0.75 alpha j hat. Okay. So that's an important result because we need to know acceleration to go to our equations of motion, right? Acceleration of the full body. Okay? So step 3, equations of motion, equation of motions, EOM. All right? Some forces in the x direction, that's just going to, and that equals mass times acceleration of the center of mass in the x direction. That's why we determine this, right? Well, the only forces acting on our free body in the x direction is AX. So we have then AX equals our total mass. Oh, let's correct this. I think we can just fix it right here, right? That is our total mass, M, as we saw, where was it? Right here. Okay? Total mass, M, times acceleration of that total mass, rigid body, right? Okay, so AX equals 2 of our mass, so 2 of our little m's, and then we've got 0.25 alpha. Okay, so once we determine alpha, we'll be able to get our reaction. But this will be what comes in part B when we're determining our reaction forces. Some forces in Y equals the total mass times the acceleration of that center of mass in the Y direction. What are our forces? Well, we've got the AY reaction. We also have our total mg. Yep, 98.1 newtons. And all of this equals 2 times our mass, negative 0.75 alpha. Once we determine alpha, we can plug that in. Okay, but we don't know alpha yet. So the alpha is going to come from summing the moments about point O. And we're choosing summing moments about point O here because none of these reactions contribute to, have moments about point O, right? Because their line of action is through that point. So the only moment we have is due to the weight. And this, once we have it, is going to be the moment of inertia about point O times the angular acceleration. That's what we're looking to solve for in the k-hat direction. And all of this, because it's planar motion, should be in the k-hat direction. Okay, so our only moment here, right hand, mirror what I'm doing with your right hand. It looks like my left hand. It's not really. Start from point O, point towards points towards the line of action of this force, the perpendicular line of action, right? Wrap in the downward direction, and your thumb should point towards you, which is in the positive k-hat direction. Okay, so we've got M, G, and that moment arm is just the x value there, so 0.75, and they're positive, right? The total moment is positive. And this then equals our moment of inertia, which we already calculated to be 8.33 times alpha. And so when we move into step 4, we're kind of already doing it here, which is to solve for unknowns. Okay, alpha, well, that's just going to be 98.1 newtons times 0.75 meters all over 8.33 kilogram meter squared. A newton is a kilogram meter per second squared. So should we check the units, right? Kilogram meter per second squared times a meter all over a kilogram meter squared. Kilogram cancels. We got meter squared canceling, and it's just 1 over second squared. So yep, this is a radian per second squared. Now we could, that's the unit calculation. Now let's do the number calculation. So then alpha is 8.829 radians per second squared. Okay, then we can just come back up to here and solve for our reaction forces for part B. So this is A. When we get into B, our AX is just 2 times our 5 kilograms times 0.25 times our acceleration, which is 8.829 rad per second squared. And this 0.25 came from it being a distance earlier, right? Is the vertical drop in the y direction there. Plug all that in. AX is 22.07 newtons. And last but not least, plug into this equation to get AY. AY is then just going to be equal to mg pulled to the other side. In fact, that total mass is in both of these, right? This equals that total mass. So we could pull that out. That's 10 kilograms for the total mass. And then we've got 9.81 meter per second squared minus 0.75 meter times the 8.829 radian per second squared. And I'll just sneak it up right next to x ay when you plug in those numbers and calculate it is 31.88 newtons. So the resultant force is the resultant reaction here points more in the y direction at this time shot, right? So we point something like that. Okay? All right. All right, so this next example, let's zoom in a little bit, maybe we can make sure we can read the problem statement, right? So this one actually comes from the book. Here we have, okay, so we have a pulley connected with two masses, right? So the one on the right being heavier than the one on the left. And now we're going to follow this in a very, we're going to analyze this in a very systematic way, but I think we kind of know that, all right, the system's going to turn to the right. But, well, on our free body diagram, I'm going to assume a positive direction, and so it's actually, we're going to assume rotation in that direction, and then we should get negative angles. But first, let's set up some important points. Let's label this mass as number 1, this one as number 2. Let's see. Important points that I'm going to label is C right in the center there. This point that makes, well, perfectly horizontal to C, kind of where the cable leaves is just going to be A and B. Okay, so that differentiates that. Okay, so let's dig into this one. Again, we're given, what is the question here? How far does a 20 kilogram mass fall in half a second? And then what is the tension in the rope on this side? Okay, between basically B, point B and then our mass 2 as I've labeled it here. Okay, great. And the pulley, we're given the moment of inertia there. Okay, anything else? No. Okay, so let's get into it. Let's follow our procedure, right? Step 1. Draw out a free body diagram. We'll just, well, let's do one for each part. Well, we'll need one for the pulley. We'll need one for each mass. Okay, so 3 total. Okay, let's write this. I'll go out like 3. 1, 2, 3, 1, 2, 3, 1, 2, 3. Yep. Do my best to do a nice looking circle. Okay, a little bit under curving there, but that's pretty good. Okay, this is point C. This is point A. This over here is then point B as we look at it, right? Pretty obvious we're looking at a side view here. Okay, let's see, what forces? Well, we've cut through that cable, so there's tension down, that goes down to the number 1 mass. There's tension over here on the right that goes down to number 2 mass. Okay, what else? Well, there's a pin here, so there's got to be a reaction that we need to include here. And in general, we need 2 reactions due to the pinning of the pulley. It has a weight, right? And that's given as, oh, it just doesn't give us the weight, so hopefully we don't need to use it, right? Okay, we'll call this M of, let's label this something so we can be careful not to confuse it. Let's call it M of C, since the middle of the disk is C. So I've just subscripted that with C, even though we don't have a value for that, unless I'm missing something, 20 kilogram mass, 10, yeah, right? So we'll just, it's just the mass there. This is why we're putting in every single force we can think of that's actually there, right? Okay, so I think that's good. So this is our free body diagram for the disk, for the pulley. Okay, let's see. We'll need 2 other free body diagrams. This is what I meant earlier, though, before we move on. I'll be assuming that this then rotates in the positive axis direction, where the axis direction is here in the positive j hat direction, right? So based on the coordinate choice, right? So I, j, and k. Okay, I think that's good. All right, so let's move on to then mass 1. And we'll do a very similar looking one here for mass 2. And they should be tied together here. Okay, mass 1 is a little bit smaller, so I'll represent it as smaller than mass 2, which is actually 5 times more massive. Okay, and the forces it feels, right, are the tension. That's the same one as above. Tension 2. They both have then weight, M1G, M2G. Okay, and again, using the coordinate direction to be our guide, we'll assume a positive upward acceleration, even though we know that A2 should then be negative, A1 is positive. Omega and alpha should also be negative. right? Just because 20 is heavier than 4. Okay. Next step in our procedure, because I think everything over here looks good. Next step in our procedure is kinematics. Okay. Let's see. Probably going to need, right? Think about force equals mass times acceleration. We're probably going to need to know the acceleration A1 and A2 in order to answer the question, which is like, how far does it go, right? That's really a kinematics question. Let's see if we can have a relationship here between the acceleration we get at 1. Well, that's the acceleration we're seeing at point A. Well, we'll make some observations as we go along, right? But we'll need to know the acceleration here at point A. Now, let's get some intuition here first. Like, what do we expect the acceleration of A to be? Well, C is not accelerating at all because that's a pinned point, right? So that one's a static, it's a fixed point essentially, right? A is probably going to be, well, like the next instant of A is going to be moving, down to here, right? As the pulley rotates along along the direction we're assuming omega and alpha to be, right? So if omega is positive, A would then be moving down to here. So just the acceleration at this point is probably going to be pointing inward a little bit while also heading downward here. Well, let's see. Let's work through this. What is it? What do we actually get? Okay, we're going to do okay, let me label this first. Kinematics, and the first thing we'll do is we'll analyze A from C, and we can do this because they are on the same body, or what's not. The choice of equation we're going to use here is the same body, rigid body kinematic relationship. Okay, so the acceleration of point A in terms of C, right, is the acceleration of C plus the angular acceleration of the rigid body crossed into the relative position vector of A from C minus the rotation rate, or the angular velocity squared, angular speed squared, position vector again. Okay. Now this is for general, for in time. This works at all time, which we need to do in order for us to answer these questions. Like how far does it fall in half a second? So we need to have expressions that are general for all general time, right? We can't just do it just at the instant shown. Okay, so let's expand this out a little bit. This is our kinematics relationship, and then we'll make some observations. All right. Well, the first thing, like I said, this is 0. This is pinned. Okay. So that one goes away. Now, this is in planar motion, so it's alpha is the vector is just a scalar times k hat crossed into the position vector of A with respect to C is in the minus I hat direction with a distance of r. And maybe I should throw that into here. This is r. Okay. Now, going back here. So this is minus r I hat. Okay, and that's it. And then we got this one. Well, that's minus omega squared minus r I hat. So then this is, because the radius is given to us as 125 millimeters in the problem statement, we'll just put it in at this point, minus 0.125 alpha. J hat, why is it negative? Alpha cross K, or sorry, K cross I. So I can't even bend my, can't bend my hand that way. Maybe I could do it. No, I can't do it. K is pointing out at us. Cross it into I hat. Thumb points up in J, but it's negative, right? We have a negative in there. So that's where the negative comes from. And then this is, well, that's already written there, but the two negatives make a positive. That one we don't need to do any cross product. That's just 0.125 omega squared I hat. Great. Okay, now time to make some observations, okay? What we want to do is relate, because you see now, what we got is that if alpha and omega are in the correct direction, right, that means that this goes down in J, it accelerates downward in J, and rightward in I hat. All right, like we said, that kind of makes sense. Like if it was accelerating this way, we know it's the other way. These will both be negative, so everything's going to be flipped around here. But this actually accelerates downward and inward to the right. Oh, and I should say, even if omega is negative, that's always going to be to the right, right? Because that's an omega squared. So maybe I don't know exactly how it's going to be pointing, but something like this. That's the absolute acceleration of A. Okay. And so then if omega and alpha are actually in the other direction, then only the j hat direction flips. So it'd be like pointing up this way. All right, which also makes sense, right? If the wheel's rotating that way. Okay. Now, let's see. Oh yeah, so we made that observation that that's where AA is. How do we then relate the acceleration of point A to the acceleration of 1? Okay. Well, A is affixed to this rigid body, right? A is a point on the outer surface of this disk. It then rotates. The rope rotates downward, and because they're attached right at this time instant, the acceleration downward is just the j hat component. Right? Well, the acceleration downward of the cable is the acceleration downward or upward if it's the other direction, right? Of number one of the mass number 1 here, right? So that's just going to be a useful observation that all we have to do is take the j hat component to get A1. Okay, so we have A1 equals A tangential j hat, right? It's really the tangential component at A is the j hat direction. Okay, so basically A1 is then going to be minus 0.125 alpha j hat. We need tangential component only. Okay. Another observation is that due to symmetry, the acceleration of B is just minus the acceleration of A. In terms of the j hat direction, I should say. Oh, no, that's completely opposite, right? Because that's on the other side. So we can make those completely opposite of one another. And all why we can say that too, and all the way that it shows up here, it's the only thing that's going to change when we go to A, the acceleration of point B, is that the relative position of B with respect to A is positive r I hat. Positive r I hat flips the sign on both of these terms. Everything else is the exact same, right? Because the angular acceleration is still the same for any point on the rigid body, and the angular velocity is the same, right? So this is a true statement. So acceleration at point B, the absolute acceleration, just flip the signs of these two terms. 0.125 alpha j hat minus 0.125 omega squared I hat. Okay? Now, because of that intermediate statement, then A2, right, is of how mass 2 is falling, relating, how do we relate the acceleration of 2 to the relation, how do we relate it to point B? Just like we related point A to mass 1, we can relate point B's acceleration to the acceleration of mass 2. Okay, it's just the tangential component. So A2 is going to be a B tangential only in the j hat direction, which is 0.125 alpha j hat. All right, and these now have a positive relationship because we've assumed that this is now the alpha is in the counterclockwise direction, which means if that's the case, B is going to be accelerating kind of like that way. And then that vertical component gives us A2, and it's in the right direction. Okay. Now let's come to let's come to this relationship here, and the top one. What did we end up getting? Right. Both of these say that all we had to do was take the radius of the wheel or of the disk and multiply it by the angular acceleration to give us that tangential component of acceleration, which gives us the accelerations of the masses. That we might have been able to just determine straight away, right? So the tangential component is r alpha for planar rotation about a fixed point. Okay. So no surprise there. In fact, this is just really confirming something we should have maybe had some intuition going in, right? Okay. Step 3, since we have our kinematics now fully described, basically all we've done is related the rotational acceleration of velocity, so all the rotational motion, to the translational accelerations of the masses, right down here essentially, right? Those are the important, these two here. Okay. All right, so let's now go to our equations of motion. Really, the S should be equations of motion. So we have equation of motions. Doesn't make much sense. Okay, I'm going to start with summing the moments about C. Right, that's a fixed point. All right, because C is a fixed point. Right, when we sum the moments, we can go to a nice, neat form, which is the moment of inertia about C, alpha k hat. Now that is also the center of mass of that round circular disk, right? Okay. So then this says that our moment, what are the moments acting on the disk? Well, these three forces, the reactions at the pin and then the weight, which acts right through the centroid, they have no contribution to the moments about point C, right? So we only have the moment due to T1 and the moment due to T2, right? The moment due to T1 is going to be clockwise, right? Position vector to the line of action. This one's going to be negative. The T2 is going to be negative. Position vector to the line of action, crossed, into the downward. Oh man, this is hard on the screen. That way, point it downward to go in the direction of T. My thumb then points downward into the page. So that one's negative. Okay, so the moments then, right, and then the distance there to the line of action for both is a radius, so 0.125 or 125 millimeters times T1. That one's positive. We then subtract off 0.125 T2, that one being negative. Both of those are in the k hat alignment. And then we have, we were given that the moment of inertia is 0.05 in the problem statement. Okay, 0.05 is the moment of inertia. We do not know our alpha, k hat. Okay, that's good, that's useful. I'm actually trying to keep clear of the kind of starring the equations, keeping track of what's unknown as we go along here, right? I mean, think here, we have, well, A1 is unknown, alpha is unknown, A2 is unknown, alpha is unknown. So we really have one equation for two unknowns. We added an unknown for the another equation here. So at this point we have three unknowns and two equations. Now we have T1 and T2, which are unknown. So we've now added a third equation, but now we have two more, so five unknowns, right? Why would we add that, right? Well, it's because what's going to happen next, our other equations of motion, we're going to sum forces for our two masses here, right? And we'll get another relationship that involves no more unknowns. Well, that'll have the mass times acceleration, and then the tension force, mass times acceleration. Those are already unknowns in our system of equations. We're not going to be making life any more difficult here. Okay, so the next equation of motion, sum forces in the x direction. Oh well. Okay, so I guess first we let's be thorough here. What if we didn't know to jump to the masses, right, and do the summing the forces in the masses, right? Let's be thorough and say, okay, well, can the summing the forces in x and y give us any information? Let's try it. Well, the only force in the x direction is just the reaction Cx, okay? And that would be adding a new unknown, right? Well, that's going to be the mass of the disk, which we actually don't know, times the acceleration, xwards acceleration of C, of that center of mass. Well, that's a fixed point, so this is just 0. So this is 0. So what this tells us is that the reaction is 0, which is true, okay? There's no x reaction, but doesn't really help us in answering the question that's being posed, right? It doesn't help us then solve for the acceleration of 2, which we then need to then integrate in time and get write a kinematic relationship for to get how long it falls in half a second, right? It doesn't help us solve for what T2 is, right? So it's interesting. I'm glad, it's a good idea to write it all down, but nothing lost, but we didn't learn anything new. Some forces in y. Okay, well, we have the reaction Cy. We then have minus mcg, that's the weight of the disk, minus T1 minus T2. Those are unknown, right? We actually don't know the mass of the disk either. And that's going to be mass of c times its acceleration in the y direction. And that, again, we got pinned, right? It's a pinned point, so that's 0. It can't be moving anywhere. It's a fixed point, right? So that's 0. So again, this would then be used to tell us what, because this one's going to be non-zero, what the non-zero reaction force is at that support, that pin support, which is mcg plus T1 plus T2. So it's going to be supporting all of those forces. But again, this will just help us solve, this will only give us what that reaction is once. So we use this to find Cy once T1 and T2 are known. Okay, kind of scribbling that in there, but it doesn't help us get to what the question of the system is. All right, so we got to find somewhere else to get more information, and that's going to be writing writing equations of motion for 1 and 2 separately, and here it'll be summing the forces in the y direction because there are no moments here. The rotational equation of motion would just be trivially 0 equals 0, let's say, right? No rotational acceleration due to no moments. Okay, so instead we dig into mass 1. Okay, it says the sum of the forces in the y direction acting on mass 1. We have T1 and mg, and then also, so we don't have to pull this back up. We have something very similar on mass 2, T2 and mass 2 times g. So T1 minus m1g, and that must equal mass 1 times its acceleration. So therefore, T1 equals m1g minus, remember now, we already determined, okay, so we're already starting to plug in some relationships here, right? We know that the acceleration of run, we can write it in terms of alpha, is minus 0.125 alpha, okay? So we'll do that here, write this in as minus 0.125 alpha, okay? And that's nice. I mean, that's a good result. That's a huge relationship. In fact, since we've used one of our equations, we're basically replacing this equation with that equation. Okay? And do this again for mass 2. Sum forces in y equals T2 minus m2g, which equals m2 acceleration 2. And so we get tension in 2 in the 2 cable, 2 segment of the cable, is m2g plus 0.125 alpha. And that's, again, we're using this information here, that the acceleration of 2 is 0.125 alpha. Plugging that in. And this now replaces that relationship. So now if we look at what we have 2 equations where the only unknowns here are T1, T2, and alpha. 2 equations for 3 unknowns. Do we have one other relationship? Yes, right down here, right? One more equation that relates T1, T2, and alpha, and nothing else. We now have 3 equations, 3 unknowns, and so let's star these. We have that one, we have this one, and that one. Those are going to be the ones that we now use to solve. So it's time to move on to step 4, which I think was solve for unknowns in our general procedure that we started this lecture video with. So 3 equations that I put a star around for 3 unknowns, T1, T2, and alpha. Okay, so let's solve them. What I'm going to do first is I'm going to take right here and no, let's do it this way. Let's take this relationship. Oh, it's not on the screen yet. Let's take this relationship and solve for T1 minus T2, right? Because we can pull out the 0.125. You'll have T1 minus T2 and get something on the right-hand side here in terms of alpha. Okay, and then the next step we'll do is take this relationship minus this relationship. We can set those 2 things equal each other. That should let us solve for alpha. Okay, so that first one, if we do T1 minus T2, on the right-hand side was 0.05 alpha, and then both of these had a 0.125 in front. And so this is 0.4 alpha. Okay, And then we take this minus that, right? We get T1 minus T2 equals, let's see, M1G minus 0.125 M1 alpha minus M2G minus 0.125 mass 2 alpha. Okay, so all of this combined, replace this left-hand side with 0.04 alpha, pull all the other alphas to this side, so then we have, mass 1 is 4 kilograms. Is that right? Yep, 4 kilograms. Mass 2 is 20 kilograms, so 4 times an eighth is a half, and pull it to the other side. All right, so that's that term. And that's that term with that plugged in. Okay, and then I'm going to pull this term. So 20 divided by 8 is 2.5, 2.5 alpha. And then what's left on the other side is just mass 1 minus mass 2 times g. And this then, right, so with some simplifying, allows us to solve for alpha. And we're getting there, right? Alpha is then going to be, this is 4 minus 20, so that's negative 16 times 9.81, all divided by a fourth plus a fifth. No, sorry, that's not a fourth. 0.4 plus 0.5 is 0.9. 0.9 plus 2.5 is 3.4. So we will need to divide by that, 3.4, and we find alpha equals minus 46.165 rad per second squared, which is interesting and useful and an important step, but again, not our final answer. What we're looking for is two things. T2, the tension in 2, which is right here. Now that we know alpha, we can find this. And then we have one other thing we're looking to solve for too. So the tension in 2 is going to be the mass of 2, which is 20 kilograms, times 9.81, that's your g, acceleration of gravity, plus the radius, 0.125, and now we plug in alpha, minus 46.165. All right, we could check the units on these. Is it still valid? I think we could. Let's see. 20 was kilograms. This is meter per second squared. So this term had better be meter per second squared. Well, this is this was originally the radius meter, and this is now the acceleration rad per second squared. So this term is meter per second squared. That's meter per second squared. This whole thing is kilogram meter per second squared. So this is a Newton after you do the multiplication. All right. Every once in a while, I like to make sure, show you how I do like the unit checks, make sure I didn't make any mistakes, and that my equations make sense. Okay. Tension in 2, and so we finally get that the tension in 2 is 80.79 newtons, and that is a final answer. So the cable in 2, in that second section down to mass 2, carries a tension of almost 81 newtons. And then we want to know how far does this mass fall in half a second. To do that, we need the acceleration of 2, right? If we can write it as a function of time or a function of position, or if it's a constant, then we can go to our kinematics relationships. Okay. Well, the acceleration in 2, remember, was just 0.125 times alpha j, and we found alpha was negative, so this actually accelerates downward, 5.765 j hat meter per second squared, and this is a constant acceleration. Constant acceleration with, well, let's say it starts at y naught, because we're just looking how far does it fall. So start it at some zero datum level. Starts with initial velocity, as we start at rest, and now our acceleration is constant, and then negative 5.765 meter per second squared, and we want to do this for a change in time of half a second, right? That is just a kinematics, actually one of our easiest ones, right? So the final y position is the initial y position, well, that's 0, plus there's a term here where it's v naught times a change in time, well, that's just 0. So the only term that's non-zero in our kinematic relationship is this one, a naught t squared over 2. Plug these in, minus 5.765 meter per second squared, times a half a second squared over 2, and we find minus 0.7206 meters. So our second, mass 2 falls 0.72 meters. All right. Okay, that was a fun one. Nice long one. Had a lot of different parts to it. Many, 3 different components to do free body diagrams for. We had rotational with translational equations of motion from different parts. I really like that problem. Okay. All right. I think we got more coming up here too, though. We're only just getting started. Okay, so in this next example, so we've got a slender pole. It's being pulled from a rope at this orientation. So it's a 3-meter long pole, slender pole, being pulled from a rope that's attached only a half a meter upward. Okay, so and then we're given both a static and a. I know it's hard to read here. So the uniform pole shown in the figure has a mass of 100 kilograms and a moment of inertia of Ig. So that's about its center mass, 75 kilogram meters squared. Coefficients of static and kinetic friction are given. So both static and kinetic friction are given between the end of the pole and the surface, as static is the 0.3, kinetic is 0.25. Determine the pole's angular acceleration at the instant this force gets applied. Okay, so, and the pole was originally at rest. So it's shown here that the pole slips out. And so that would mean that we are into the kinetic friction situation here. But also notice that we're just analyzing, really the only system we're analyzing is a straight up and down in the instant after the pull happens. And really just we have to then determine through our analysis whether it's a static or kinetic friction situation. So we kind of have to consider both scenarios here as we do our work, or you could go down the static friction route and then do the check when you get there. But we'll do it as we go along, because the analysis doesn't actually change too much between the two cases. And if we keep it completely general, we can do basically two of them at once. Okay, so let's start with the free body diagram, as always. And again, all we're analyzing is the scenario where it's straight up and down. So let's do 1, 2, 3, 4. Let's put our center of mass there, and then 1, 2, 3, 4 more. Okay, so there's my slender pole with the center of mass. And okay, let's label this point down here as A. This point here in the middle is G. This point is unnamed. Okay, let's put our coordinate system on here. So we'll use x or xy, and we'll put it down there at A. That's the origin of our coordinate system. Okay, and then along with that we have our unit vectors as always. Good to just put them on here. Remind ourselves if we have to do cross products later on, hey, we got a little coordinate system there. We can put our fingers along a certain direction and wrapping in other directions with the right hand rule. Okay. I'm also going to put we need to put the forces on here, but we'll also be putting the lengths. So the whole thing is 3 meters, where to the center of mass then is half of that. That's 1.5 meters. And then when we go up a half a meter, so it's going to be a third of this. So what's a third? Like right about there. That is half a meter, 0.5 meters. And that's where our applied pull is going to be. And so that means that the rest of this is 1 meter, right? Okay, I think that's all the geometry in there. Let's now get our forces in there. What are the forces? Well, we got the gravity acting through the center of mass. We have our normal force. We have associated with that a friction. Oh, I'll just put it there like it's stemming off of it. It really acts as a contact, but that works. And then we have our applied pull up here. And we'll just call that P, and that's a 400 Newton force. Okay, great. Now, like I said, we don't know whether this friction is of the static variety or the kinetic variety. So let's label our two cases that we're going to analyze. Case 1 will be where the bottom, so point A, stays put, and we have static friction acting. And case 2 is the friction of when it's moving, so slipping out. bottom A for case 2 slides out. But again, we're just analyzing what the angular acceleration is at this time instant that we have shown here. So actually, we're not analyzing anything about the motion there. It's just what the angular acceleration is, right? Because think about it, right? If you pull here, either the pole goes that way, right? Because you're pulling that way, or the bottom slides out, and then it rotates like this. And because the picture shows you it's like this, you kind of expect the kinetic friction scenario. But we are going to analyze it and see which case it is. Because if you haven't pulled hard enough, or you've pulled too high up, it's gonna stay static and pull, and just kind of go like that. My hand is in the way. Just gonna go like that, kind of act like a pin, right? Okay, that'll show up, right? Okay, so then next step 2 is then kinematics. And by the way, these steps, you don't always need to do them in order, but it's just kind of a recommendation, like write out all your kinematics. Because let's see if we can relate A and G, and these are on the same body, the same rigid body. So we analyze them like that, right? So A, G, the acceleration of the center of mass is the acceleration of point A plus the angular acceleration of the rigid body, the slender pole, and then the relative position of G with respect to A minus omega squared RG with respect to A. Okay, what can we cancel out? This we don't know, right? That depends on if we're in case 1, this is 0, but this is definitely 0. And again, we're just analyzing this time instant here. So we're at rest. So there's no angular velocity. In the next time instant, there will be an angular velocity, and that comes from the acceleration. But at this point, this is, we're right before the pull. We're at the instant of the pull. Okay, so now this is going to take on 2 varieties, right? In case 1, right, this is going to be the acceleration of G is then, and so case 1 is where the acceleration of A is 0. Okay, so the acceleration of G is just alpha k hat crossed into, now the position vector to go from G, to go from A up to G is 1.5 in the positive j hat direction. 1.5 j hat. Okay, and k hat cross j hat is minus I hat. So AG for case 1 is going to be minus 1.5 alpha I hat. And we'll give that a nice dashed box, because we'll probably be referring to that later. The other scenario, case 2, is where, well, the acceleration at A is not 0, because it slides. And so we need to include it in our we can't cancel it out, essentially. So AG is then just going to be, it's going to be exactly this from this term, but then we'll just have an acceleration of A. And that's only going to be in the I hat direction, right? A can only A is sticks to the floor here, so this is the acceleration of A minus 1.5 alpha in the I hat direction. Okay. All right. So now we move on to number 3, step 3 in our analysis, which is our equations of motion. Again, equation of motions, or EOMs. So let's look at, let's do the summing the forces first. So sum of the forces in the x direction. Let's see. We got our applied pull, and we've got our friction. Okay, so this equals, once we write them out, this is going to be the acceleration of G in the x direction. And that's why we did this, can we relate, right? The acceleration at A to the acceleration of G, because that's how we're going to link it together with our equations of motion down here. This is always the acceleration of motion of our center of mass. Okay, so we have our applied pull minus the friction force equals the mass times acceleration of the center of mass. This now, and then this is case 2, might become important if case 1 isn't valid, if we determine case 1 is not what the system is experiencing. So that's going to come from here, right? So we're going to have to break this up into 2 cases. Case 1 is going to be where P minus F equals, the mass is 100, and then we have minus 1.5 alpha. And case 2 is where P minus F is 100 And then the only added term there is the acceleration of a, minus 1.5 alpha. Okay. And here we've used the information from above, and so this equation kind of replaces it. We've added some more unknowns, but we're starting to build some relationships. I'm going to label this as equation number 1 here. Okay. It's really our equation of motion, the first one that we wrote, so nothing special about 1, just as the first one we did. Sum of forces in the y direction is mass times acceleration of g of our center of mass in the y direction. Okay, and this equals 0, right? And right, and so that's just from observation, right? There's no acceleration in the j hat component here. Right, so then our normal force must balance our weight force, as those are the only two forces in the y direction, in the vertical direction there. Okay, so normal equals mg. We'll probably use that when we, right, that'll be used, that's what we're going to be using for the friction force here. All right, but first let's get that third equation of motion in here. That's the sum of the moments. We'll do sum of the moments about the center of mass g. And so that's in the k hat direction. And so this is our moment of inertia about the center of mass times angular acceleration. And so then, let's see, what are all the moments about g here? Well, the weight has no contribution, no moment associated with that, no normal force, but the pull and the friction do. Okay? So the pulling force, r vector, cross it, wrap your fingers in terms of p, that is a positive moment. Whereas r vector into friction, we're wrapping our fingers this way, my thumb then points into the page, that's a negative contribution to the moments, right? Summing the moments. So we have our positive p times 1 is kind of our moment arm, minus the friction force, which has a moment arm of 1.5, and then that equals what's given to us in the problem statement, that the moment of inertia about the center mass is 75 kilogram meters squared. And that's all times alpha. Okay, so this is the result that stems out of the third equation of motion as we've written them or ordered them. So I'll label this one 3. Let's get the second one into something, more useful, which this says, this is going to tell us that the friction force, which is, well, let's do this in this other color to highlight it. The friction force, which is our friction coefficient times n, so this equals mu mg. Okay, so this is useful. Let's star this. This is now completely known if we're in a certain case. So case 1 is going to be mu s. Well, this is going to be the max, right? This is going to be the max friction force. So let's be careful with this, right? So here, what we're saying here, case 1, we have mu equals mu s, and this really is a maximum force that could be provided by friction. Mu s mg. And so what we need to determine whether we're in case 1 or case 2, whether we have static friction or kinetic friction, is the force provided by friction greater than this? And if so, then we've moved into case 2. Okay, and where case 2 we'll just plug in mu k there, and that's not nothing about a max. That's just what the friction force is while it's sliding along. Okay, so let's solve here now. Okay, which is step 4. Here, let's assume we're in case 1 until we see evidence that we are not. All right, you always stay static until not. I'm going to start here with, and this is my relationship number 2 up here. So 1, 2, and 3. Let's start here with relationship number 2. Which says that our F max is 0.3, that's our coefficient of static friction, times the mass, which is 100 kilograms, times gravity, which is 9.81 meter per second squared. This is 294.3 newtons. Okay, if we then look at number 1, it's up here, this says that our friction force is the applied pull plus 100 times 1.5 alpha. Okay, we don't know alpha or the friction force. So let's see what 3 tells us, right? 3 tells us that we have P minus, now the friction force we can plug in this relationship. So this is going to be 1.5 times p plus 100 times 1.5 is 150 alpha. Okay, so this is just F. And that must equal 75 alpha. Okay, so we can solve this. This says, here we have p minus 1.5 p, so that's minus a half p, equaling, over on this side we have 75 alpha, and then we're going to add to it how much more alphas do we have. We have 1.5 of 150, so that's 75 more, so 225 negative. We add that to the other side. 225 plus 75 gives us 300 alphas. Pull all the alphas to that side, you get 300 of them. So this means that alpha is, and p is 400 from the problem statement. So this over here is going to be negative 400 newtons. This is going to be negative 200. We have 200 divided by 300, right? So we should be able to figure out that alpha is minus 2/3 radians per second squared. And there's no problem with that. All right, that could be our answer. In fact, we would be done. You might want to dox that and say, hey, we are done. We just found alpha. But the problem here is that the force that would need to be provided by friction for this case, we can then check, right? We can plug this back up into number 1. The force is then 400 newtons minus 150 alpha, which turns out to be plug in 2/3 there, and evaluate this, you get 300 newtons. Okay, so this says that in order for this to be alpha, from the static friction case, the friction force has to be 300 newtons, but this is too big. All right, the needed force for this scenario is bigger than the maximum force that could be provided by static friction, and so we are in case 2. So let's write this out. What this says is that friction force is greater than max static friction before slip occurs. So the pole slips. So pole slips, and we have case 2. So we are in case 2, and we need to analyze that, right? So basically the work is, well, we don't get to use the result, right? No, definitely not a waste. Nothing's a waste. We've got a lot of good information there, right? One thing you could have definitely done is tried to just rewrite the relationships in terms of F right away. You just gotten this, and you wouldn't have ever come up with what would be the final answer if this was true, and that way you're not ever at all at risk of boxing the answer and moving on, right? Because this isn't the right answer. All right, but we're just going to follow the same procedures here. Case 2, we'll start with the second equation, which says that our friction force is now 0.25 times 100 kilograms times 9.81 meter per second squared, which is 245.25 Newton, right? The kinetic friction is always you have to pull. You get enough force to overcome static friction, and then the kinetic friction actually lowers down a little bit as the system starts moving, and so you don't have to, right? The actual friction force provided here is a little bit less than what it was for the max static friction, right? Than what it was when we overcame it and the pole started to slip. Okay, go to the third equation. This says that, let's see, we'll just solve here for alpha. Alpha equals, from the third equation, alpha is going to equal p minus 1.5 f over 75. All right, and we can then we can just solve this, right? So this says that this is 400 newtons minus 1.5 times 245.25 divided by 75, and we get our angular acceleration to be 0.4283 radians per second squared. And that's it. That's the answer here. Let's see. Yeah, determine the pole's angular acceleration at this instant. All right. So you might then ask, well, whatever happened to number 1 here? How come we never used it? Well, number 1 for case 2, right? is right here. Oh, I went too far. Number one relationship for case 2 had an AA in it that wasn't there for number 1. So you had like an extra equation to use for case 1, and that's because this was really a max force, and you had to have that condition that the force from friction wasn't bigger. Right, so it was an overposed problem. Not really overposed, it's just this is the maximum friction force. Now case 1 is used to solve for the acceleration of A, which we could do, right? That's the actual, the rate at which point A accelerates to the right. I might as well just do it, right? We got room at the bottom of the page here. Acceleration of point A is then P minus F over 100 plus 1.5 alpha. So I'm just solving this for AA, P minus F divided by 100, add over the 1.5 alpha, and you've got A, the acceleration of A. Plug all that in, so this is going to be 400 minus 245.25, divide that by 100, add 1.5 multiplied by the alpha that we just found, 0.4283, and we get the acceleration of A is 2.19 meter per second squared. Okay. All right, that's it for this one. We got one more. Okay, we got an example here. I'm going to actually try to zoom in a little bit further just for the problem statement. We got a pendulum, okay, that has a uniform 5 kilogram plate right here at the end and a 2 kilogram slender rod. Kind of a small picture here. What I want to determine is the horizontal and vertical components of the reaction here at O that the pin exerts on the rod at this instant when theta equals 30 degrees. And also we're given that omega, so the angular velocity is 3 radians per second in that orientation. So it's rotating currently in a counterclockwise fashion. So about a positive k-hat axis out at us, right? Okay. So what I like about this one is it has a composite shape, right? So we have to work through a problem here. And so I think we'll have our first step here, which is a free body diagram, but also maybe put like a 0th step over here, which is determining these the composite shape stuff. So putting 0 as the number, the step number. I don't know. Oh, not GM. What is this? Is the center of mass and then the moments of inertia. Okay. Right, because this is, we always have the composite shape. We have to do a little bit of work. So let's reproduce kind of the diagram here and treat it like a free body diagram. Very slender rod. Okay, and then a plate. Now, did I draw that to scale? 0.5 and then 0.3. Not too bad. Okay, well, I should have drawn that more of a rectangle, but that's pretty good. Okay, I think we can work with this. Now let's see here. This is 30 degrees. Okay, what else can we say? Let's label the parts as, the slender rod will be number 1 and the rectangular plate will be number 2. And then let's see, do we know where then the next step is going to be where, when we determine the center of mass, each one's center of mass. Well, yeah, that's right in the center there, and this is going to be right in the center of the slender rod there. And so if the whole thing is, 5, well, let's do it here, right? This to there is half a meter, and then here to there is 0.3 meter, right? Yep. And well, then we also have 0.2 meter. I'm just kind of reproducing what's in the picture. This then is going to be 1/4 of a meter, 0.25 meter, and this is from point O. We haven't even on this free body diagram put any forces yet. It's because we need to know where to put them, right? And think about the mass. That's the only thing acting on this are the reactions and the mass. I need to know where to put the masses. That's what is governing all of this work here before I actually put the forces on there. And this is going to be 0.65 meter, and that's because we go the whole 0.5 and then another 0.15 meter to get to the center of mass there. Okay, So we've done this kind of along this line here. Maybe this axis that we have drawn is kind of like, I don't want to think about it the x-axis because we're definitely gonna work in the traditional Cartesian, but maybe this is the x prime axis or something, right? Okay. So what we want to do is actually determine, now we don't know where this is, but probably going to be somewhere in between. This center of mass is going to be pulled, because there's a long slender rod here, and this one's going to be pulled heavily this way because there's a rectangular mass. It's probably going to be somewhere about there-ish. This is going to be G, or our center of mass, for the entire composite shape, about which we have the weight of gravity acting, right? So let's see. This here is going to be the total mass, right? So M will be the total mass of the two combined. And then that would be mg acting downward. And then the only other forces on this shape are the x reaction and the y reaction at the pin. Okay? So I said step 0, although I kind of drew out the whole free body diagram there. Our center of mass, where does it go, right? What we want to determine is what is that distance? Okay, and I'll label that here in a second once we're done. Okay, so the center of mass is going to be, it's just going to be along this, so along x prime. And I say it's, x, y is the regular Cartesian. This is the x prime, okay? So then we can do this, right? We can choose any axis about which to calculate this, right? And so the way this works is, right, take the mass of, element 1, which is 2, multiply by where its center of mass is, 0.25, from the origin here. It's actually negative. And then plus 5 kilogram is number 2's weight, mass of 2. Actually, we can add it to our list of information here, right? M1 is given as 2 kilograms. M2 is given as 5 kilograms. Okay, we got 5 kilograms, and this is now negative 0.65. And then divide by the total mass, which is 2 plus 5. Okay, 7. 0.5357 meter. Oh, and that's negative. And again, this is along x prime, or along 30 degrees from O. Alright, so now we just found out what this distance is here, right? 0.5357 meters, and yeah, it's a little bit more than 0.5, so it's actually into the rectangular plate, just slightly, as we've drawn it. Okay, you might think I knew that going in. It's because I did. Okay, now we're going to need the moment of inertia about O, and this is a composite shape, right? So this is going to be the moment of inertia about O from shape 1, plus the moment of inertia about O from shape 2. All right, that's going to be, well, this is just now, for shape 1, that's just at the end, right? So we have, from the table, we have a relationship, that's M1, the mass of 1 of the slender rod times its length divided by 3. That is, now I have appendix C here, sitting here, all right? So if we're looking here, it's on the first page, slender rod, we want the moment of inertia about O's axis, so either the y or the z axis here, that's 1/3 ml squared. And we actually derived that in 2 lectures ago. Okay, and then we have now the moment of inertia for 2, so this is right here. Moment of inertia for 2 about O, we're going to need the parallel axis theorem here. First, this is a big rectangular plate. Okay, so big rectangular plate, we are taking the moment of inertia about the z-axis, right, to go through our center of mass. All right, so let's first write this down, right? This is going to be the moment of inertia about its center of mass plus, and then we're going to do parallel axis theorem, right? So the moment of inertia about its center of mass is going to be going through the z prime here. I of z prime is 1/12 mb squared plus h squared. That's the 2 dimensions of the rectangular plate here. Okay, so we've got a 1/12 mass of 2 b squared plus h squared. We'll plug those in here in a second. That's just going to be 0.2 and 0.3. And then we got the parallel axis theorem to get us from this axis up to that. All right? And so this is going to be m2 times the distance. Well, the distance between is just that 0.65, right, to go from there to there. Okay. So a little bit, right, this is the rectangular plate in Appendix C through its center of mass, and this term comes from the parallel axis theorem. Alright, so we're ready to calculate this now. Let me zoom out just slightly now that we're into our work here. Okay, so I naught, or I about 0.0 here, plug everything in, we got 2 kilograms, 0.5 meter squared divided by 3, not going to be so careful with units here, 5 kilograms, 0.3 squared plus 0.2 squared plus 5 times 0.65 squared, and so moment of inertia about 0.0 is 2.33. Once you calculate all this, I think it's 3 repeating kilogram meter second squared. Okay, so we got our geometrical properties, we got our free body diagram. We are now ready to get into kinematics and our equations of motion, right, or for dynamic analysis. Okay, so number 2 here, we'll go to kinematics. And what we'd like to do is relate the moment of inertia about, or not the moment, the acceleration of g, right? That's what our equations of motion, the translational ones, are going to be written in terms of the acceleration of g, you know, acceleration of gx, acceleration of gy. So we need to relate that to the point we have a lot of information about, which is 0.0, that fixed point here. Okay, so you have the acceleration of g is the acceleration of 0.0 plus angular acceleration of the rigid body crossed into the position vector of g with respect to o minus omega squared. That's the angular velocity of the rigid body there, the composite body, and then relative position vector of g with respect to o. This is the only thing we can cancel out, and that's because that's pinned. Okay. Now, let's see, the position vector of g with respect to o. Well, okay, this has, right, this is now the distance to go from O to our center of mass, but it's a long 30 degrees. Okay, so this is actually going to be, the vector is going to be minus 0.5357 meters, cosine 30 degrees in the I hat direction, plus sine 30 degrees in j hat. Okay, we'll separate our work. All right, so we got our components, right? So that's now starting from O. How do we get to G? All right, you go down and backward. We can use that 30 degree, right? Cosine is going to be the horizontal movement, and then the sine, which is opposite in that triangle, is going to be downward. Okay. Now, okay, so let's actually do this, right? So acceleration of g, okay, we're going to need kind of this space down here. Acceleration of point g is going to be the angular acceleration k hat crossed into this long thing, right? Which is, I'll write it out again, minus 0.5357 cosine 30 degrees. Now cosine 30 is root 3 over 2, so might as well just, could we just do that? Why don't we just do that, right? This is root 3 over 2 I hat, and this is a half j hat. Okay, doing quick check. Yep, that should work. And then minus omega squared negative 0.5357. Again, we have that same term, root 3 over 2 I hat plus an half j hat. Okay? So that means that our x component of acceleration is going to be, what are the x components here, right? Well, we know that we have the I hat component over here, but let's figure out that over here we have to cross with our position vector with k hat. So that's going to come from the k hat crossed into I hat. And so we have our x component is going to be k hat crossed into k hat crossed into j hat, which is going to be 1/2 alpha, and that is then negative, right? K cross j hat is going to be minus I hat, but we have that negative right there. Okay, so in the end, this term is going to be alpha over 2 times 0.5357 plus, and why is it plus? We have the I hat is what we've got, a negative and a negative. Okay, so plus a root 3 over 2 omega squared, and then 0.5357. Okay, and just checking my work. I think it all looks good. Now the y component, right, it's going to be the other components here. So we have k crossed into I, that's positive j with a negative sign in there. So this is going to be minus root 3 over 2 alpha 0.5357, and then plus, because again negative negative, plus 1/2 omega squared 0.5357. Okay, so one thing to note, we have the omega, but we need the alpha. Right? This is 3 rad per second given in the problem statement. But we need alpha. Okay, and we also need to relate this to the reaction forces which are coming here, right? The first thing we need to do is to get what alpha is, and then we know that through our equations of motion we'll be able to get there. Okay, so equations of motion, EOMs. First one that should get us that angular acceleration, summing the moments about O, because we don't have much, right? The only force that doesn't go through point O is gravity, because it's kind of this freewheeling pendulum here. So it's just going to be mg crossed, position vector crossed into mg. Okay, so right, remember this is to get a moment we do position vector crossed into mg. And so that's just going to be the horizontal component of the position vector, which is the cosine, cosine 30 degrees times the 0.5357. Okay, so our only moment about O is going to be mg times the horizontal, or the I hat component of the position vector, which is 0.5357 cosine 30 degrees, which we know to be root 3 over 2. And that must equal the moment of inertia, which we already calculated, about 0.0, times the alpha that we're looking for. Quick check, we know this, we know everything over here to the left, we should be able to solve this, right? So alpha is then 7 kilograms, that's m, that's the total mass of the entire composite body, times g, 9.8 meter per second squared, times everything in the middle there, 0.5357 root 3 over 2 divided by 2.333, that's our moment of inertia, kilogram meter squared, and we get alpha equals 13.6554 radian per second squared. Okay, now we can go back and get our accelerations up here, right? So acceleration of g, that's the acceleration of the center of mass, and once we plug that in we get 7.833 meter per second squared. Acceleration of the center of mass in the y direction is minus 3.9245 meter per second squared. Okay, very important quantities. So we are accelerating downward, right, which makes sense, and to the right. Quick look at our free body diagram. Does that make sense? Our acceleration would then be somewhere, and it's more to the right, so acceleration is that way, right? Makes sense. More to the right, and then slightly downward as well. Okay, more equations of motion, right? This is our first one, summing moments. We also have our two summing forces. Some forces in the x direction. The only one we have is OX, right? The x reaction force, which is the total mass times the acceleration in the x direction, and we have all of that. So this is 7 kilograms times the 7.833 meter per second squared, and so OX is 54.8 831 Newton. That is one of our final answers. And the last equation of motion, summing forces in the y direction. We have our y reaction force in the upward j hat direction, minus mg, that's acting downward, and that must equal our mass times acceleration in the y direction for our center of mass. And so therefore our y reaction force is the total mass of g plus the acceleration downward. Okay, which is 7 kilograms, 9.81 meter per second squared, minus 3.9245 meter per second squared. And plug all that in. So reaction is 41.1985 newtons. Okay, we've reached the end of this one. Okay, I like this one again because it dealt with composite shapes to get our moment of inertia, but also like once we have that, right, who cares what the shape looks like? It's just a center of mass with a moment of inertia about a point of interest, right? And then you can work through the equations of motion just like anything else. Okay, lots of examples here in this video. Hope you made it all the way through. Hope you got a lot of benefit out of this. And we're ready now to move into the other kinetics methods with work energy and momentum going forward.